So we would like to explain what we mean by a direct sum of abelian groups. So let us begin with two abelian groups. So let A comma B be abelian groups. And we're going to denote the operation for both groups by a plus. And we define a direct sum with B as a set to be simply the set of all pairs of elements where A belongs to A and B belongs to B. And what happens here, so this is the notation for direct sum. Sometimes people will call it an external sum because it's built between two sets that do not correlate in any possible way, at least a priori. And the operation is defined in a very natural way. So if you have two elements of this set, then you perform the operation coordinate-wise. So you take the sum of the first two elements and the sum of the second two elements, and you put them together, which means that the opposite of AB is going to be minus A comma minus B. Of course, maybe it should be a little more natural to say what the zero element is going to be, the neutral element. So the neutral element is going to be 0, 0. Sometimes what people will write here is they will write 0 of the group A, comma 0 of the group B. This is to remove any ambiguity about what these elements are, because strictly speaking, the 0 of the one group has nothing to do with the 0 of the other group. But sometimes we simplify the notation by saying that by denoting both of them by a simple 0. And the opposite of AB, as I was saying a moment ago, is going to be minus A comma minus B. So we call this an abelian group. And I'm sorry, we call this the direct sum of the abelian groups A and B. And we can easily now define also finite powers of a group. So A to the n will simply be A direct sum with A, or I should say first that we can define this for more than one group. So A plus B plus C, direct sum of A with B and C, will be all triples of elements, each one coming from the corresponding group, and the operation being defined again coordinate-wise. And of course, if we can do it for 3, we can do it for any finite number. Somebody might ask here, how about infinitely many groups? It can be done even in that case, but there are some interesting distinctions that one makes in such a case. And plus, we don't need any of these things in our study, so we're not going to go over to infinitely many components. What we would like to say is that if we take the same group and we take its direct sum with itself a few times, then we come up with the power of a group. So, for example, to give an idea here of what we're talking about, z squared will simply be the set of pairs of integer numbers. Okay, and the operation is defined coordinate-wise, and it has all the properties that we noted above. So we will see that in our study, we will be particularly interested in groups of the form z to the r direct sum with z over n1z, and so we will have finitely many components here. So this is the kind of typical group that we're going to encounter because, for example, it can be proven that the set of the group of rational points of an elliptic curve defined over the set of rational numbers has this form. And when we say it has this form, this is again something that we should try to elucidate, and we will do that in a subsequent video. But that's what we mean. That's what we mean by taking direct sums of groups. Thanks for watching.